consider the simple circuit below. Now, this circuit is important for two reasons. You'll do a lab experiment with this circuit, and it's also common enough in the exam. Well, also it's an important circuit for reasons that'll become clear in a moment. But let's have a look at this circuit. Very important circuit. Here is a fixed resistor. This guy? Ammeter, voltmeter, something. Variable resistor. What's great about this?
You can change resistance.
Yeah, and here is
A
battery. I suppose the only thing missing really, there should be a switch. But anyways, I'll redraw this and I want to talk about the important parts of it. So this is a circuit you need to know off by heart. Now it doesn't have to be exactly like this, but anyways, I'll draw my version. So I like to have the resistor at the bottom. And then here is the ammeter. And then here is the battery. And I'll put my variable resistor here. It really doesn't matter. And if I got everything, I need a voltmeter. I'll put my voltmeter here. But you know, it's not a big deal. You need a voltmeter, an ammeter, a resistor, and a variable resistor. That's what you need. Okay. So my first question is, what happens as the resistance in the variable resistor increases from 0 ohms to a higher value? So let's have a look here. Which way is the current flowing? It will flow from positive to negative. So the current goes along like this. Okay? I don't know what the voltage here is. Doesn't matter. Let me call it E. Okay? Now there are two voltages in the circuit after the E. There's this voltage here, which is V. And then there's a voltage here which we don't measure. What letter will we give it? Let's give it some name, like we'll just call it X. Alright? Now, are you happy if I say the E must equal the V plus the X? Are we okay with that? Yeah? This X here is a voltage. Okay? If I use the triangle VIR, the V here is the same as the I multiplied the OR. Okay, so you could say E equals V plus I, and I don't want to use the same letter OR, so I'll use a small OR. Okay? So I have V equals E minus I OR. So if I set this guy at the beginning to be 0 resistance, what will this voltmeter display? E. So for example, if this was a 10 volt battery, then here we'll say 10. What will happen if I start to increase the resistance here? What will happen to this voltage? Decrease. Okay. So my point here I'm making the job of this is to change that. Okay, the reason you have this variable resistor in this circuit is because you want to be changing the voltage across the resistor. That's why you have this, okay? By changing the variable resistor, you can make different voltages here. And then you notice as well, when the voltage changes, you also see this changes. And then you notice this changes too. So, I don't really care that this is E. What I really care about is the V and the I. Because what I'm going to do now is make a graph. Okay? Before I continue, you need to draw this circuit. You need to know this circuit, because there could be an exam question where they say, what is the circuit necessary to measure current and voltage through a resistor of change in voltage.
What's the name of that circuit?
I don't know, it doesn't really have a name, because the question would usually be like, a student wants to measure how current changes as a result of a change of voltage.
Okay.
Draw a circuit that lets them do this. You got that drawn? Now look, that's the way we'll do it in the lab. This is the old-fashioned way. If you're rich, you can do it easier. You can have a device which lets you vary the voltage. So you can actually set what voltage you want on the machine. Then you can just connect it to an ammeter, connect it to the resistor, and then connect it back into this. So, that would be much simpler, but it's also much more expensive because having a machine where you can set whatever voltage you want isn't exactly cheap. Whereas this is, it's in the other room. Do you know that piece of wood I have with the wire on it? Do you know the one in the room? You know the one I'm talking about? It's on the ground, a piece of wood with the wire on it. That's the variable resistor. Yes, yeah. So I meant that myself. I'm quite proud of it. Okay, continue. Yeah. So here is an example of some data. You see your voltage, it begins at 10, like I said, and then as you increase the variable resistor, what happens to the voltage? Decreases down. And what happens to the current at the same time? Decreases as well. Okay? Let us plot this data. It's an important graph in physics and electricity. But before we plot it, which way around do we put the values? Which goes here and which goes here?
The one goes.
Which one is this? V or I?
V.
Yeah, why?
Because we're changing.
That's it. Because the V is the thing we changed, that goes on the X. And then we saw also a change in I, so that goes on the Y. Okay? I'll give you a moment to plot this. It's a very simple plot. You can tell what shape you'll get from looking at it. What shape will you get? Linear, yeah. So let's have a look at this. Can you plot this, please? It doesn't have to be perfect. Make it pretty good. Oh, good job, Gina and Harry. You're using rulers. Although it looks like Harry never used that ruler. It's still in his packaging. Yeah. Oh, I see. You keep it extra clean. Very nice. See, he respects his ruler. I think you did something wrong, Lynn. Your shape looks wrong. When the voltage is... okay. Don't worry, Lynn. Half the students do that mistake. Oh, come on, Diego. This isn't that bad. I'm just asking you to plot this.
Today's not my day.
Ah,
I
Diego.
have 4 hours of sleep.
Oh, Diego.
Not wrong.
That sounds like plenty to me. Let's have a look, Zach. What's your graph looking like? Ah, come on, guys. I don't need a work of art.
I'm Spanish. I'm Picasso.
I don't know about that, Diego.
Trust me.
Okay, I see one graph done. There we go. Axis not labelled though. Axis not labelled, Lynn. Axis
Oh,
not labelled.
not labeled.
Label, give it a name. What is on the x-axis? Ice cream sales? No, no, no. What's on the x-axis?
Is it V?
V. So write V somewhere.
It's right here.
Where?
It's right here.
Oh, for goodness. Okay.
Okay, it's right here.
No, no. Put it at the bottom, in the middle.
Ah.
No, no. Yeah, there. There we go. And where's the eye? Oh, no. Put it on the side, nice and big, so I can see. There we go. Yeah, okay, that's better. Right. Okay, if you plot this, let's see. Dorian, yeah, good. Gina, can I see? Can I see? Gina? Oh, Lynn, tell her what went wrong. You made a similar mistake, didn't you?
Yeah.
Yeah? You did it backwards. It should be going up, shouldn't it?
Yes.
Yeah? Yes? I told you, it's coming. Can I see, Harry? Let's see if you got it. Yeah, okay, good. Diego?
Because it's just little dots, but yeah. That's fine.
Okay, Zach? Yeah, okay, so you all got straight line graph going up. Yeah? Okay. This is an important graph. It's called the IV characteristic for the resistor. So just to be clear, the IV characteristics of a resistor is the plot of the current and the voltage when you vary the voltage. Okay, so you need this. So Diego, you were asking me what the name of the circuit was. It doesn't really have a name as far as I know. But this graph that you drew does have a name. This graph is called the IV characteristics of the resistor.
So I wanted to ask,
Yeah.
because I shown this in the laboratory, is when you say you plot something against something,
Y against X.
Y against X.
Yeah. So we're plotting I against V.
But then when you say the relationship or the correlation, you say X against Y.
No, I don't think so. I think it's always Y against X. I think. Man, I'm hungry.
You
No.
use
No, where is it?
your Y
No, don't tell me I lost it. My voucher. Oh.
Why didn't you say it on your phone?
No, 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 no! Don't. Oh no!
Yeah.
Oh my.
Free lunch.
It's supposed to be a really big card, so
Oh, I promised Sylvia. Oh wait. Don't panic. I found it. Nice. All right, thank goodness. Sylvia will be so mad at me because I promised we'll do Uber Eats today. Right, okay. Do you have that written down? Yeah? No, not yet, Diego? Okay. Has any of you heard of this term before? Dorian? No? Harry? No? Zach? No?
Not current voltage.
Yeah, I noticed for some reason this isn't something that's always on high school electricity topics, chapters. I don't know why, it's not that difficult, it's just a plot of current and voltage, so I'm not sure what the big deal is. Yeah. Do you know the meaning of the word characteristics?
Yes. Property.
Like a property, like a feature, like a description nearly.
Defining.
So this graph is going to be different for each resistor. And that's important, okay? It's different for each resistor. Continue? Yep. Now, Ohm's law states that. Now, before you write this down, does anyone know what Ohm's law is? You don't? Okay. Ohm's law states that for some material at a low voltage and a low current and a constant temperature, the IV characteristic graph will be linear, passing through the origin. Okay? So, before you write that down, what Ohm said was, okay, Ohm said that if the V is small, and the I is small, and the temperature is constant, then your graph will, be linear, at least at the beginning. Okay? But the moment the voltage gets too big or the temperature starts to change and the graph's behavior starts to change, like maybe you get more current, maybe you get less current. It depends on the material. Okay? Before continuing, remember we have VI or. So what does or equal? V over I, which for this graph would be 1 over the slope. So for example, let's imagine the graph goes like this. Would you say the resistance is getting bigger or smaller? Here the resistance is constant. But here what happens? It's bigger because it's 1 over the slope and the slope is getting to 0. So, and what's happening if the graph turns this way? The resistance must be getting smaller. Okay? But what Ohm noticed was for most materials at low values, all graphs will be linear. Okay? Some people make the mistake, teachers included, of thinking that this formula is Ohm's law. But it's not. Okay, this formula just comes from our triangle. Right? So some teachers say, oh, this is Ohm's law. It's not. That's just the definition of resistance from the triangle. Okay? Ohm's law is a statement about the characteristics. It's linear. So Ohm said that for some materials at low voltage and low current and a constant temperature, the graph will be linear. That's the definition of Ohm's law. And I'll give you a little secret. When I'm interviewing physics teachers, this is a question I usually ask them in the interview. You know, I would usually say something like, explain to me how you would explain to students what Ohm's law is, then I can see what they say.
So that's if we want to become a physics teacher.
Yeah. Yeah, yeah, yeah. And you know, this is one of those things that a lot of physics books get wrong. There's a few things I've noticed in physics and maths books that are common mistakes made by the author. So physics, it's this. Maths, I can think of a couple of examples. I saw an outrageous example yesterday in one of the A-level books or something. Let's see if you guys get it right or wrong. What does this equal?
Plus or minus 3.
No,
It's plus 3.
just plus 3. Yeah, yeah. It's definitely just plus 3. It's not plus minus 3. And 99% of maths books will say it's 3. But the A-level book or whatever I was looking at yesterday said plus minus 3, which I just thought outrageous. Huh?
Why?
Functions are only allowed to have one value answers. You know, you're not allowed your function to have 2 answers. Now, don't be confused. This is a different question to x squared equals 9. That's an equation. What's the value of x? Plus or minus 3. But if I simply said to you, what is the square root of 9? The definition is the square root of 9 is the positive root. That's the definition of square root. It's not anything else, you know. You get the idea? You know, so like these are common things that you sometimes see that are wrong in books. And this is one of them. Okay, this is Ohm's law. Continue. Now, Ohm's law isn't always true because you notice the language in Ohm's law is very, do you know the word hedge? Hedging? Hedge, do you know this word? Do you know hedging? No? Not plants though. Hedging in English means you're not being pinned down to one meaning. That's what's happening here. Ohm's law states that for some materials at a low voltage, what exactly is low? And a low current, what exactly is low? You know? So it's not exactly a really formal law. Do you know what I'm saying? It's kind of a little bit vague. And it's not even always true. It's not always true. In fact, some materials won't be linear, even at a low voltage and a low current. Okay? So, if it is true, then we describe the resistor as being ohmic. And if it's false, we say it's not ohmic. So, the graph you drew for me, are we describing that as ohmic or not ohmic? Ohmic. Okay. You want to note this adjective here. I know, it's stupid. I can give you an example. Like think about what's happening here. I could make up the law. I could say, all students in my class, I should say, some students in my class will do well. If the student does do well, I'll call them a Stevenic student. And if they don't do well, then I'll just call them a non-Stevenic student. You know, like it doesn't seem too useful because you don't even know if it's always going to be true for your resistor. So if you said, okay, well, is Diego Stevenic or not Stevenic? I go, I don't know. I'll find out later. You know, it's not exactly Newton's second law. Okay. Right, continue. So, we already looked at what the slope represents. What does the slope represent? 1 over resistance. Yeah, okay? Oh, and the units then, if it's 1 over resistance, then the units would be for the slope 1 over ohms, per ohms. Yeah. Yes, okay. You wrote this down, didn't you? The slope is 1 over r. You all have that? Maybe it's worth writing it down again. Oh, okie dokie, you got that? Diego? Harry? Yeah? Okay. Now, let's have a look at a question. You would like to know the IV characteristic curve of a filament lamp. Draw the circuit. Okay, we don't need to do that because it's the same as the circuit I drew earlier, except for one difference. What would be the small difference? If I was, yeah, what would it look like?
Circle with an X.
Yeah, it'd be like this. That'd be the only difference. So, use the table below, draw the appropriate curve here. So I want you to draw this. And then, in a moment, we'll calculate the resistance. But first, can you all draw this? Now, before you do you think this will be linear? Let's see. So the voltage starts off at 1, and now we have 2. Then when we go to 2, we have 4, and then 3, we have 6. So what's happening here? Plus 2. Yeah? Plus 2, plus 2. Ah, now what happens? Plus 1, plus 1, plus 1. Now? Plus 0.5, plus 0.5. So is it a straight line? No, it's going to level off. Okay? So let me see your graphs, please. Give this a draw. Well, it's more of a curve. I want you to do it a bit more freehand. Lynn? Beautiful. Gina, how's your graph? Beautiful. Beautiful. Right. Where the heck are the labels on the x and the y axis?
I have to label it.
Of course you have to label them.
Give me 2 seconds.
Let's see, Dorian, how's this one? Yeah, okay, nice. You got the labels? Labeling right now. So I think everyone has the same graph. It flattens off. Okay? So, the next question is to calculate the resistance. So what's the formula for resistance? It's V over I. So what I want you to do is to make, can you look up? Make another row here, or, so we'll start from the easy one. What did I say? V over I, wasn't it?
Yeah.
Yeah, so that's 0.5, 0.5, 0.5, 0.5, 0.5, not 0.5. Can you give me all the ors here, please? Right, what are the resistance? Let's start down this end. So what's this, 0.5? And then here, what do we get? 0.54. Next? 0.58.
0.62. 0.67.
Yeah.
0.71.
Right, so what's the smallest resistance? And the largest? Yeah. Is this material ohmic?
It is up to.
Yeah? Yeah, just make sure you give, what's the word, caveat, is it? It's ohmic until 5 volts. Right? 5 volts? Yeah. So, it's ohmic until 5 volts. Yeah? Fair enough? So, you know, this is a nice exam question if you get it decent. Continue. Now, in the example of the filament lamp, would it matter if we run the current backwards? Would anything change? Apart from having a minus current. You know, if you turn the battery around, would anything really be different apart from your values being negative?
In this circuit?
Yeah.
No.
No. The lamp doesn't care which end the current goes through, so it doesn't matter.
This is maybe a pole LED.
Yes, this is what we're getting to. So for a simple ohmic resistor or a filament lamp, no, it doesn't. It doesn't matter. So, in you know the graph you did earlier for me, the first graph you did, VI, it was like this. If you run the current backwards, the only difference is you get negative values, so it doesn't matter, same numbers, okay? And the same happens with the lamp. What happened with the lamp? The lamp went, I'll put it here, no, I'll put it steeper. On the same graph, there's your lamp, and then it levels off, okay? But the same thing happens in the other direction. Again, it doesn't matter, okay? Which I've drawn for you. So in the exam, please be careful. They also want the negative values. What I mean is they could ask a question like, sketch the IV characteristics for a lamp. So what they want to see is the student drawing this in their answer book. VI, so you get marks for having them the right way around. And then they want to see a straight line here, and then level and level here. Sorry, let me just deactivate this. Relax them. And that's an example question. Now, if we try to do the same thing for something like an LED light. Now, do you know what LED is? Yeah?
Those care about.
Yeah, they do care about the direction. So, where the heck's an LED? Do we have an LED anywhere?
The back of your phone, flashlight.
They're LEDs?
Yeah.
Usually, yeah.
Oh yeah, of course, they're LEDs, right. So like this LED light, right? It does care which direction the current goes in. There is an in and an out. Does matter. So can you look here? Okay. When the voltage is going through the correct way, what's the resistance at the beginning? Big or small? No, the other way around. At the beginning here, it's level. The slope is low. If the slope is low, then the resistance is big. And then what happens to the resistance later when the voltage is higher? The resistance becomes small. Now that's interesting. That's interesting. The more voltage you put through the LED, the less resistance you get. Now that's unusual behavior. Most materials do not behave like this. Like your lamp, when you put more voltage through it, you get more resistance because it gets hotter. Okay? LEDs are quite special in that they have an opposite behavior. As you put more voltage across it, you get less resistance.
Does it have a pain point?
Oh, it must burst at some point, yeah. I'm not sure what it will be. But notice what happens here. If you try to force the current backwards, the resistance here, big or small? Really big. In fact, it's so big, hardly any current is passing through it. In fact, it almost acts like a wall. You know, if this is the LED, the current goes in, and you get your current, and the resistance gets smaller as you pass more through. But if you try to pass it through backwards, then, you get so much resistance, there's no current really. But if you really try really hard and have a lot of voltage, then at a certain point, it breaks. And then all the current starts to flow. Okay, so it's a little bit like, I always think about it like a door, like this door here, you know. So if you're going the right way, you know, if you're coming in, then the current can pass through. But if you try to pass the current the other way, then the current doesn't pass. And if you keep trying, at some point, I'm going to break this door open, but not today. In the exam, they sometimes ask you for this graph. Now, they're a little bit of a jerk here because they do want some numbers on it, but there's only really one number that they want to see. They want students to know that for these LED lights, This point here, where it goes from high to low resistance, that usually happens around about the 0.7 volt mark. Okay. So in the exam, to get full marks, you need to mark this off as a 0.7 volt. Did I give you the symbol for the LED at the start of this chapter? Didn't I?
Triangle with the
Yeah. Now, why do you think it is a triangle?
because it can be-
Yeah, it's to show you which is the right direction, isn't it? Right?
So could LEDs work with alternating current?
Oh no,
No.
no. I think if you stick an LED onto an alternating current, in effect,
Strobe.
yes, in effect, you're making it, you're converting the AC to DC.
Yeah.
But usually alternating currents have large voltage, so you'll probably break the LED. Yeah. But LEDs is a very simple way to change an AC to a DC. Because basically it blocks the reverse direction, so, but it doesn't provide a constant voltage. So what will happen is, instead of the current going like this up and down, it'll just go up and to zero. If you mix an LED with a capacitor, you could smooth out the bumps.
Do you have to label all of them?
The most important thing to have labelled on it is the X and the Y. And the 2 points you need for the exam, please listen, the 2 points you need labelled for the exam is this point here, called the threshold voltage, which is about 0.7. And this point here, which I guess is different for each material, is called the breakdown voltage. I think LEDs and these semiconductors and all this were developed around about the 60s or 70s. They're made out of silicon. They're really important. It's really important for computers, this material.
At the start, they couldn't figure out how to make an LED white. They just had blue.
It's difficult to make white LEDs, and most LEDs that are white aren't exactly white. They have a sort of a hue of blue maybe to them or something. But the great thing about LEDs is that they're very, very efficient. Because think about what's happening here. As the voltage increases, the resistance decreases, which means the current can pass easier through it. You know, so they're really efficient. So in my home, I have LED lights. You know, and they are only rated at 5 watts instead of 60. So like the LED light in the kitchen, it's a 5 watt light bulb, not a 60 watt light bulb.
Right.
I mean, it's just as bright. Yeah. So they're just really, really efficient. But like you said, Diego, one problem with them is they're not properly white. You know.
Have to mix them together to get
Yeah.
that.
Yeah. And the other thing is they're more expensive. So like, you know, my LED light bulb, I think it costs something like €4.
Spy ones, cry ones.
Yeah.
But then
The
they
last
last
two
way
will save you money.
I don't think they last way longer. I think they last a little longer. I think the claim that they last way longer is exaggerated.
But then you get also revenue on your like decreasing.
It's a bit decreasing, but I mean, look, the thing is, I remember when I was a kid, you could buy 10 light bulbs for €2. Okay, so now I have to pay €4 for one light bulb. Seems very expensive to me when I can still remember buying a pack of 10 light bulbs for €2.
So you have to adjust for inflation.
No, even adjusting for inflation, it still seems very expensive to me. Yeah. Guys, in your home countries, what's the situation with light bulbs? Is everybody using LEDs in their home country, or is anybody still using the old filament light bulbs? What about, would you know, Dorian, for back home? Probably
In
LEDs?
South Africa, we still use
LEDs?
we still use paraffin lamps in South Africa.
Okay, so not LEDs then.
Yeah.
Diego?
In my home, like, yeah, we use LEDs, but then for all things, sometimes you can't use LEDs, so we have to buy.
Which ones?
Like old lights and stuff.
Old light.
Old lights.
Oh, the old ones. Oh, yeah, of course, yeah. What do you think? LEDs back home for you? Harry? LEDs? Okay. So everybody's using LEDs at home then, really.
It's kind of like turn lighter and lighter when you turn on.
Yeah. Some of the older LEDs take a few minutes to get to the right color. Yeah, although the new LEDs are faster.
The thing about LEDs is that you can't dim them, I think.
No, you can now. Because in my living room, I got a dimmer LED. Yeah, now it doesn't work perfectly because as you turn the dimming switch, you don't get a nice transition. It's kind of a bit, yeah, it's a bit jagged, you know. But still, you can now get. You're right. Originally you couldn't, but you can now get LEDs that you can dim. Yeah. But like I said, it's more graduating in stages than a smooth altering. Now, this topic here, how many questions do you have in the database? Only 6? Okay. Can you try those for a few minutes and then we'll see how you get on. What we'll probably do is maybe get a start on the next topic after you try these for a few minutes. And then I'll move ID 277